Hey, you want to know the one thing that I really love about NASA? No matter how good something is, NASA personnel are always striving to make things better.
That's right, Johnny. Exploration and discovery seems to be hardwired into everyone who works at NASA. The status quo just won't do. Hi, I'm Jennifer Pulley.
And I'm Johnny Alonso. And today on NASA 360, we're going to show you some examples of how NASA is continuing to explore and understand the challenges of tomorrow. All right, so as I just said, at NASA there's this intangible quality that many of the people who work here have. Let me explain. Everyone seems to have this passion to take on these complex challenges and solve them. The perfect example is right behind me. In a recent episode, I showed you how researchers were working on new hardware that may one day be used in space. Although the equipment they had out here last time was good, the testing showed the NASA crew how to make these vehicles even better. So once again, I traveled out to the Black Point Lava Flow in Arizona to see what NASA researchers are working on this year for the Desert Research and Technology Studies, or DRATS for short. Since 1997, NASA researchers have been conducting the DRATS field tests. These types of tests are important because it gets the researchers out of the labs and lets them judge their hardware in a real-world environment. Another element being studied this year is something called the PEM, or Pressurized Excursion Module. No matter where the astronauts of the future land, they will need housing that protects them from the harshness of space, while also providing some of the comforts of home. I spoke with Dr. Scott Howe to tell me more. Scott, thank you so much for having us out here today, man.
Sure.
Right behind you, the HDU. Tell us about it.
Well, what we're trying to do is we're trying to figure out how people can learn how to live in space. And basically, this is one of our first attempts to create a home or a residence and laboratories that we'll be able to work on the moon or on Mars or a planetary surface. Okay. That could also inform how we live in deep space as well. What we've got here is one module of several of a planned lunar outpost or a Mars outpost that we're going to test out today on this whole analog exercise. There's a team of us that are going to be studying a variety of different modules, which will be essentially the beginnings of a house or even a town that will be on the surface of another planet. This particular module is what we call the Pressurized Excursion Module. You see on the side of the module, the Habitat Demonstration Unit. That's the name of our project. Okay. And our project, we will probably test out a variety of modules, but this year we're doing Pressurized Excursion Module, which is a module that will be carried by the athlete. And the Pressurized Excursion Module, well, the reason that we use the word excursion is because it will be carried around by the athlete and it will follow the rovers, and that's what we're simulating this year in the analog.
The materials that you use for the HDU, I mean, will it be the same kind of materials that you use on another planetary surface?
This particular one is made out of fiberglass, and we have metal ribs. This module is insulated just like one would be on the surface of another world or in deep space. Gotcha. And we also have a certain amount of protection that we're doing from dust, which you would find on the surface of another planet.
So Scott, I mean, how would you power something like this on another planetary surface?
Yeah, so the unit that we have here is just using off the shelf. We have a generator going and things like that. Eventually, we'll be using both solar panels and fuel cells. But eventually, we're going to evolve into a more flight-like ECLSS system. The ECLSS system is the Environmental Life Support System, and that's the thing that provides the astronauts with air, keeps the right temperature inside.
Let me ask another question. Let's talk about docking. I mean, how do people get in?
Yeah, so there's a couple of ways to get in. The major form of what we call egress or ingress is through the rovers, where the astronauts will dock their suits to the wall of the rover and climb through the back of the suit to get in and out. However, on the PIM, we have an airlock that's right here on the end where they climb up on the what we call the EVA porch into the airlock, pressurize that airlock with air to get in and out.
Wow. Can you take us inside?
Absolutely. Let's go, Johnny.
Perfect. Oh, wow. Oh, this is cool. It's nice and cool in here.
Yeah, it's great.
So
yeah,
where are we right now?
So right now we're in the airlock,
Yeah.
and you can see there's a grill on the floor. This is part of our dust protection, where we have the crew come inside and they stomp off their feet. There will be an air shower.
Okay.
Also maybe a vacuum cleaner that they can kind of clean themselves off a little bit.
What's going on here? Can we go inside?
Yeah, sure. This is how we enter into the module right here. We go
Lead the
through
way.
here,
Yeah.
and we've got around the perimeter of the module is a series of workstations that we've been putting together. A lot of teams have done a lot of work on this.
Sure.
Over on the side here, this is the suit maintenance workstation,
Okay.
where we'll be able to bring the suits inside and work on it. You can see just to the side of that is the hatch. The hatch is where the rovers will dock, and they will be able to just pass right through and pass right on into the rover.
Very nice.
This is a general maintenance workstation. You can see there's a crane overhead where they can work on the equipment, bring that inside when they need to have a nice shirt sleeve environment for that.
Sure.
Here's the what we call the veggie unit, and it's a hydroponic garden that we're testing out how to grow plants in space. You can see it's kind of got a reddish tint.
Yeah.
It's the LED light is actually bringing out certain aspects of the plant just using that tint of light. Hopefully by the end of the mission, the astronauts will be able to have a little bit of lettuce with their food. Right next to that is the MedOps station. You can see there's a bed there that if someone is in trouble, they could relax onto that and have another crewman who happens to have that skill for medical can work on and take care of the health of the crew.
Scott, thank you so much. I know that you said you wanted to pass the mic over to Cindy, right?
Yes, and
Yeah.
Cindy is right over here. She's our scientist working on the geoscience workstation.
Very cool. Hey, I'm here with Cindy Evans and the HDU. How are you?
Fine, thanks.
Thank you so much for having
Yeah,
us.
welcome to the HDU.
This is really, really cool. Tell me a little bit about you and what you're doing with the HDU.
Okay. Well, I'm a scientist at the Johnson Space Center, and there's a core of scientists there, including people who supported the Apollo missions. And one of the things that we're trying to do is work out new science operations for conducting geological traverses on other planetary surfaces, the moon, Mars, near-Earth objects.
Sure.
So the rovers are out doing their traverses every single day. They're collecting a lot of samples. And when they come and they dock to the HDU,
Yes.
we know they're going to collect more samples than they can bring back home. We know there's going to be some really tough decisions that the science team is going to have to make in order
Right.
to bring samples back home.
Right.
So we designed this laboratory to help do some preliminary examination of the samples so that the scientists have more information so they can make those decisions. They can prioritize samples. They can know a little bit more about what they might be bringing home.
Gotcha.
So this is the GeoLab. It's designed after the curation glove boxes that we have at the Johnson Space Center for the moon rocks.
Okay.
But we had to make some modifications. We had to fit into our little pie slice, and so it's got a real funny shape. It's
Yeah.
a trapezoidal
Lots
shape.
of room here,
Lots
right?
of room. So the big thing is that we've got these little antechambers, 3 of them, 1, 2, 3.
Okay.
They're like little mini airlocks,
Okay.
and they punch through. Actually, on this outside camera, you can see where they come through on the outside.
Oh, this is what we saw from the outside.
That's exactly right. That little back porch
Oh,
there.
okay.
So
Yeah.
our crew members, they're gonna when they dock to the HDU, we're gonna
Right.
ask them to go out in EVA, get specific samples that
Okay.
they may want to analyze.
Sure.
They're going to open up those one of those little mini airlocks. One's an inbox, and then once they've transferred the person on the inside in a nice, comfortable shirt sleeve environment can
Right.
retrieve those samples and.
Oh.
Oh, we got a mail delivery.
Look at this.
Look at that. So we have an inbox, we have an outbox.
Okay.
Okay? So when we get the sample inside,
Okay.
then we have a mass balance. I should put these back on. We have a mass balance where we can weigh the sample.
Right.
We can take measurements of the sample. We can photograph the sample with these overhead cameras. And then we can put the sample on this this stand right here, this is a microscope. And then I just acquired an image. And then we can put a little scale bar on that image, and it's saved as an image file that the science back room can actually drag over and look at. So that the crew members will be talking to them and saying, well, look, I see these really cool crystals, and the science team may direct them to look at a different place.
So here's a question. I mean, why do we have to study these rocks from other planetary surfaces?
Well, one thing that rocks from other planetary surfaces tell us is something about how the solar system was formed. We have rocks on the Earth. We understand a lot about rocks on the Earth. We have just a small number of rocks from the Moon. We have no rocks from Mars except for some meteorites. We need to have those rocks, look at them, understand their chemistry, understand their forms, be able to say something about the solar system formation.
Cindy, thank you so much for having us in the HDU today.
It was a pleasure.
It was awesome. Hey, this is NASA 360. We'll be right back.
Of course, every year at DRATS, researchers attempt to expand their knowledge from previous years, and this testing season is no different. For this go-round, the DRATS team upped the ante and brought 2 rovers to help them prepare for future missions.
The SEV rovers, or Space Exploration Vehicles, are revolutionary spacecraft that will help humans explore much more than we ever could before. Building on lessons learned from the Apollo mission rovers, NASA has created these pressurized vehicles to help our astronauts do more meaningful research in a much more comfortable setting. For example, when the Apollo-era astronauts wanted to use their rovers, they would first have to go through a lengthy suit-up process, then spend as much as 8 hours exploring on one long spacewalk. This approach had several downfalls. First, spacesuits both then and now are very bulky, cumbersome, and can be painful to use over a long period of time. Secondly, astronauts only have a small amount of oxygen that they can carry on their backs, limiting the amount of time they can spend on the planetary surface. Luckily for crews of the future, the new SEVs were built with those limitations in mind. Future astronauts can now sit comfortably in a shirt-sleeve environment and drive the rover within inches of a rock or item of interest. If they do need to get out and explore, they can simply climb through a hatch into a suit that attached to the back of the vehicle. Within minutes, they can be on the surface exploring. The process of getting into their spacesuits and out of the vehicle is now faster than ever, enabling multiple short excursions as an alternative to one long one. Of course, another huge benefit of the SEVs is the mobility they provide. Astronauts driving these vehicles can explore as much as 200 kilometers in any direction, greatly increasing the scientific opportunities during the mission. To help prepare for these future missions, planners at DRATS brought out 2 vehicles and crews to work in tandem with each other. Complex docking maneuvers, communication tests, and numerous other activities were done to help validate mission procedures and help planners find any unforeseen problems early on. Because all of this testing and experimentation is being done in the real-world environment here on Earth, mission planners can make changes and tweaks to the vehicles to make sure they are ready for missions into space. The same technology that will someday be used by astronauts in space could also lead to better, more efficient transportation back here on Earth, too.
If you've watched this program before, you may have seen me talk about something called the Athlete. Well, when we first saw it, it was just a small demonstrator. Now, with updated hardware, it's even closer to being flight ready. I spoke with Julie Townsend to find out more. Julie, it's good to see you again.
Good to see you,
my God, I think the last time we saw you was in Washington with NASA 360. And the last time we saw Athlete, it's like grown.
It's definitely grown. We've gone through a lot of changes over the last couple of years.
Tell us about it.
Well, this is our 2nd generation prototype, and the big change is that it's a half-scale prototype of what we wanted to send to the moon, right? So the one that you saw in 2008 in Moses Lake was a 3rd scale prototype. So this one is a lot bigger, and in fact, if you look back at some of the pictures from 2008, you'll notice we're carrying the same habitat mock-up there. And now it actually looks like it fits, whereas it looked like it was, you know, it made our old robots look like little Tinker Toys crawling around underneath it, yeah. But the other big change with our 2nd generation prototype is it's actually made out of 2 triathletes. So triathletes are 3-legged versions of athletes. 2 3-legged robots with little triangular decks and 1 rectangular cargo pallet that carries the habitat. This allows us to set the habitat down on the ground and then drive the 2 3-legged robots away from it so that they can then go pick up another cargo somewhere else.
Julie, tell us, special features. What does Athlete have?
Well, one of the things that you can see here, well actually that you can't quite see here, is that there's another joint of the leg tucked inside the first big thigh.
Okay.
And that allows us to stand up to a height of 14 feet to the cargo deck. We used this last year to do a demonstration with a half-scale mock-up of an Altair cargo lander for the moon, where we actually got up on top of it and showed how the Athlete would unload cargo from this Altair lander by reaching its legs all the way down to the ground and then crawling off the lander.
Any other upgrades since the last time?
Well, it's got a lot more torque. It's a lot more powerful robot. Weighs probably about twice as much as our old robots did. We've upgraded our power system in the generators that we use here for the field. But of course, that's not lunar-like either. The cargo pallet would carry power generation equipment on the moon, but it would probably be fuel cells or solar panels or something more like you would use for a space mission.
Right, right. So, I mean, testing, what are we doing out here today?
Well, the purpose for us of this test is to show the traversing capability of Athlete. We've done lots of demonstrations of tool use with the limbs where we put scoops and grippers and stuff on the end of the limbs and we use them as robotic arms and stuff like that. We've done demonstrations of climbing down things, climbing over things, carrying things. But one thing we've never really demonstrated in great, distances is that Athlete is also a traversing vehicle. It's going to take that cargo and drive it all over the moon to wherever the lunar program wants that stuff. So we have just finished traversing 20 kilometers from our base camp over at Black Point Lava Flow to this outpost location here. This is not a Speed Demon vehicle. This is, I like to call this the covered wagon of the lunar program, right? So it's got all your delicate materials in it, and you don't want to shake them up too much. So you just take it at a low speed. It's the tortoise to the LER's hair.
What's your low speed?
Well, our top speed is about 2.5 kilometers an hour. So that's something like a little between 1 and 2 miles an hour. So it's not a Speed Demon. It's a slow and steady wins the race kind of vehicle, but it can go over all sorts of terrain.
Really?
Yeah.
I mean, you can move this thing like down to the millimeter, can't you?
That's right. That's another really cool thing about this. Even though it's a big workhorse, it's going to be designed to carry 20 metric tons of cargo on the moon. We can actually adjust the legs to such precision that we can align them with each other to within under a centimeter.
That's unbelievable. Julie, thank you so much for your time today. Good luck with Athlete. Oh, it was great. Hey, this is NASA 360. We'll be right back. So in mythology, we've all heard of the centaur, which is half man, half beast. Well, here we have the beast. Darby, where's the man? Or are you the man?
I'm the man.
How are you, man? Good to see you.
Good to see you.
Talk about this. Give us some information.
You're looking at what we call Centaur 2,
Right on.
our latest unmanned rover.
Really?
You've been here with me a few years in a row, and we've always had rovers out here, but on the manned version style. So what we're trying to do now is look at small, compact, maneuverable rovers that are unmanned for missions potentially that would be precursor missions, for example, that would go to various planetary bodies and do exploration, but wouldn't necessarily require a human in the loop.
Now, how is this powered?
Well, so in the center of the body, we've got a bunch of batteries. That provides all the power for the motors that control this robot. The drive motors are all located in each one of the wheels. Steering comes from a very similar motor design. Actually, all the motors and all the mechanisms that control those are identical. So it's a very redundant system. We're trying to go for a system that is easy to take care of.
Okay. What kind of accessories can you attach to this thing?
Well, so looking at this end of the robot, we've got a mechanical arm with a bucket on it.
Yes.
One intended purpose of this would be to exercise in situ resource utilization. So basically we go to another planet and we take the elements there and we try to produce energy from that. And so this bucket is one demonstration of how we would collect samples from another planetary body and actually do something with them. Another example would be a Robonaut, very human-like, dexterous robotic device. The intent there would be to have this dexterous capability built into a mobile base, so you can send this unmanned rover to do very manned-like tasks on another body.
Why would we need a robot that's shaped like a human?
Well, it doesn't necessarily have to be shaped like a human, but be able to perform like a human.
All right.
Humans have a lot of special capabilities, and if you're going to go to another planet to do exploration, a human would bend over, for example, pick things up, hold it in their hand, do a visual analysis of what you've got, and so a robot that's very human-like can do those very same things, but without the dangers, the inherent dangers involved in sending a person to that other planet. So the robot can use camera systems that determine what it is it's looking at and make some assumptions and think for itself, basically. So it simplifies things for the control.
Where would Robonaut go on the Centaur?
Well, so you can see an awful lot of real estate, flat real estate on top of the vehicle.
Yes.
Various payloads could go there. Robonaut itself would go in a location similar to where the bucket is now. Actually, it can go on either end. It really doesn't matter. While we're out here, we thought we'd experiment and try various things. Test out the vehicle, test out various implements that are on there. So it could actually go on either location, but its design location is on the front of the vehicle.
Oh, no kidding.
So we've got 4 wheels on the ground.
Yeah.
Each of those wheels can lift up and push down so that we can change the ride height of the vehicle. It lets you go over rough terrain much easier. But in addition to that, with Robonaut being on the front of the vehicle, basically it's like a human being on the front of the vehicle.
Right.
And we can actually tilt the body up or down.
Oh, wow.
So it makes the range of motion of the robot much higher and much lower. So it can do high-level tasks or stuff down on the ground.
Yeah.
It just makes it much more capable.
All right, so once this lands on a planetary body, I mean, what are we looking at lifespan-wise? I mean, weeks, months, years?
Well, the intended design life cycle would be at least 5 years. That's what we're really shooting for.
Really?
So you really want your stuff to last a long time. And you never know, we might run across a gas station up there. Maybe somebody landed there first. I don't know.
Darby, it's been a pleasure. Thank you so much for your time.
You're certainly welcome.
See you
Thank
again,
you.
right? Definitely.
I hope so.
Third time around.
Yeah, you're right.
As you can see, the DRADS crew has once again brought future-forward thinking off the drawing board and into the field. Hey, thanks for watching. For Johnny Alonso, I'm Jennifer Pulley, and we'll catch you next time on NASA 360.
It seems like everyone seems to have this passion to take on these. I mean, what would you, would this be the same? Let's do that again. Yeah. I'm Johnny Alonso, and today on NASA 360, we're gonna show you. Here comes a nice dust wind. I'm gonna stay on your side. Yeah, dude, looking like Pigpen all the time.
Probably by the end of the mission, they'll be...
Let's do that again.
For this go-round, the DRADS team upped the ante. They used 2 rovers.
To the Black Point lava flow in Arizona. Find out what NASA researchers are working on this year. Put 2.